So as you may have noticed, we've been covering each topic lately by functional groups. So reactions that make these functional groups or how to react these functional groups. And today's topic is ethers and epoxides. Ethers and epoxides we've certainly made before, but they were overlapping with, for example, the alkene chapter or the SN2 chapter. And so there's certainly overlap, and it reinforces those old concepts as well. Now, ether has an interesting history. It was the first anesthetic used for surgery, and prior to the use of ether, surgeons in the 1800s would try other techniques like hypnosis and whatnot to try to alleviate pain so that their surgery could be successful. The surgeon that is credited with using ether successfully in surgery to render the patient briefly unconscious was Crawford Long, a young physician that was described as a ether frolic, which means he himself used the drug recreationally, not to the point of unconsciousness, but apparently it was something that was dabbled with back in the day as a alternative to alcohol. So that's clearly been discovered to be unsafe, and it was probably a bigger thing when there was prohibition. So it was sometimes used as a substitute, but albeit an inferior one. So just to remind you what the structure of ethers are, that kind of helps us understand reactivity. Remember, so we have I'm using a space filling model from Spartan here just to kind of give you an idea, and this one is our traditional kind of ball and stick model. So ether, the middle one is dimethyl ether. So there are methyls and ether, oxygen in the middle. So COC bond. And when we have that sp3 hybridized oxygen, we still have it bent. So it's got kind of that same shape as water, right? Notice that sulfur, bigger atom. But if you look at the periodic table, it's right below oxygen. And so they behave, not surprisingly, in a similar way. Sulfur often makes two bonds, and when doing so, it has a similar geometry. So in this chapter, you're also going to see sulfides. So let's uncover these now. We have the structure showing up here. So sulfides will be mixed in with this chapter simply because they behave in a similar way. There's ether, and finally our cyclic three-membered ring ether, known as epoxide, that we know too well now. So sulfides are also known as a thioether. So you might see those names for them interchangeable because thio is kind of got a Greek root, thion for sulfur. So sometimes we see thio used in naming sulfur-containing compounds. So if it's a thioether, it's an ether, if you look at ether, where the S has replaced the O. And so notice these, it's a SCSC versus COC versus COC, but the cyclic joined back together. Now, we actually have made ethers before, so I'm going to say recall, because this is actually repeating something that we did before, but we're just going to kind of focus on it again. So we have made ethers. What we need to do to make an ether, in other words, a carbon-oxygen bond, is to use oxygen as a nucleophile. And so that means that if the carbon-oxygen bond was made, we could either have made it from this, made that one as our new bond, or this one. So our goal is to come up with the two starting materials that would do a good job making that ether. So let's see if we pick the red path. In other words, everything on this side of the red line was one starting material, and everything on this side of the red line was another starting material. So I'll write the whole thing in red. So that means I had ethyl, and then let's put a leaving group on there, because with an oxygen nucleophile, which would have been this piece, we need a leaving group because we're basically going to do an SN2, right? So we've learned that. So this is just bringing back some old stuff. To remind you that we made a lot of different functional groups with SN2, so you might not even realize that ethers were on your list of possible functional groups until we kind of reminded ourselves here. So we do an SN2, and voila, we get what's in the box. So that's one way to make the ether, but we could have also made the new carbon-oxygen bond on that right side where the green disconnection point is. So what would that look like? That means that everything from here on is one starting material. In other words, it's a ethoxide instead of a propoxide. So ethoxide. Plus, now we have the leaving group on the other side of the green squiggly line, and so we're doing an SN2. So these are both possible, right? Now, there's a question that's posed if we said, hey, we want to make this ether. How can we do it? We say, well, there's two ways. The obvious next question is which one's better and why. So if you think about what you need for an SN2, we like to have backside attack that on a less hindered substrate. So if we look at our substrates and we just look at the degree of substitution, we can see this is a primary alkyl halide and this is a secondary alkyl halide. So clearly, once we get to that point, we realize that route number 1 would be the best. That would be the highest yielding for SN2. Because remember that if we do not have a primary alkyl halide, then we have a strong base like an alkoxide in the presence of something other than primary, like secondary, we're actually going to have E2 as major as opposed to SN2. So if we want SN2 as the major path, then we want to go this way. Now, just to kind of, we've gone pretty far with functional groups in this class, so we always want to keep those connections in mind for the sake of any syntheses that we're doing. So another question, that's the point of this prompt down here. How can we make the starting materials that we need for this reaction, starting from alkyl halides? So starting from alkyl halides. So remember that we can already use the alkyl halide for step 1, that is ethyl bromide. But if we want to make the starting material that we need, this other guy right here, if we want to start from alkyl halide, we can eliminate, right? Do an E2. And then we have to get alcohol there. And then we have to do a simple acid-base reaction to turn an alkoxide. So sometimes for syntheses, you're asked to start from a specific type of starting material. So in this case, it's saying, how could we make everything that we need for this starting from alkyl halides? Well, this already is one, so I guess we could say that we started with one already, but this one is not an alkyl halide. So how would we arrive at alkyl halide arrive at an alkoxide from an alkyl halide? Go ahead and start here, eliminate, and hydration, Markovnikov hydration, followed by deprotonation. This gives us our nucleophile to react with our substrate. I'm going to write a general template for that reaction we just did to make an ether. So if we have some sort of alkoxide and we add a alkyl halide, preferably primary, then we get an ether. This is called, you've done this many times, but you didn't know you're doing a name reaction. This is called the Williamson ether synthesis. So since we are revealing the name associated with this name reaction, I always like to pull up a little bio if the information's available. And so here is Dr. Williamson with his side pose. And Dr. Liebig was granted his PhD, or hooded as we would say, the hooding ceremony, if they did that back then, from with Justus von Liebig back in the big group of German chemists over there that were real big in organic chemistry. So he's really famous, and a lot of famous scientists originate from his lab. Yeah, it's interesting what a small world chemistry was back then, and even still is today. It seems like everyone knows each other, but they're all kind of interconnected. So we're going to use the Williamson ether synthesis. Remember, alkyl halide, alkoxide, makes ether. Okay, so holding true to the pattern we've kind of done so far is we'll do a little nomenclature of this functional group we're focusing on. We're going to focus on ethers. And you have dealt a lot with this specific ether. This is an epoxide functional group, but if it's just a standalone molecule, a three-membered ring with oxygen in it, we call these heterocycles because they have a heteroatom in the cyclic structure. Other cyclic structures we worked with prior to epoxides were just carbon containing. So oxirane is actually the standalone name for this molecule. So that's an oxirane molecule, but if it's part of a bigger molecule, then it's an epoxide functional group. And another one we've used before, cyclic ether, is THF, which stands for tetrahydrofuran. Now, why would it mean that? Well, we're going to learn about furan in just a minute. And it has to do with how many hydrogens it has. So we'll just draw them all in. So this is THF. The four-membered cyclic ether is called oxetane. And then the five-membered ring that has two pi bonds, and they are in resonance with a lone pair. We're going to say they're conjugated. That is called furan. That's a famous one. And so that is related to tetrahydrofuran. So furan has 1, 2, 3, 4 H's. THF doesn't have those pi bonds, so it has 8 H's. So in other words, it's furan with 4 more H's. So that's hence the tetrahydrofuran. Okay, this 6-membered ring with 2 pi bonds is called pyran. That might sound familiar because pyranose is the sugar carbohydrates that have the 6-membered ring with an oxygen. So they're certainly related. When we have 2 oxygens in a 6-membered ring, that's a dioxane. But notice that the oxygens can go in different orientations. We could have them next to each other or on the opposite sides of the ring. So notice if we number one of the oxygens starting at 1, then we'd have what's called a 1,4 relationship to our oxygen. So that's depicted in the name 1,4-dioxane. We can name the substituents. Let's do a couple practice ones. So look for the parent and treat the cyclic part as the parent. So this is a type of dioxane. This is a type of furan, for example. And then we look at what's attached. And we're always going to number starting at oxygen because it's higher priority than carbon. We want to give oxygen the lower numbers possible. So if I give the oxygen a 1, and then I know that I'm going to have some sort of furan, I want to give that ether that's hanging off at the bottom the lowest number possible. So if I number 2, 3, I'll get a lower number than if I went the other way, which would have been, 1, 2, 3, 4. So the black path works out better. So we have a 3, and then we have an ether. Since the ether is a substituent, it's a methoxy group. OR, we've done methoxide before, but now it's attached. It's not an anion, it's methoxy. So 3-methoxy furan. Let's try to name this dioxane, and just for switching it up, we also put on a functional group. So we want the lowest numbers for oxygen. We know we're going to start with a 1 for oxygen. So let's try this way. 1, 2, 3, 4, 5, 6. Or we could have done 1, 2, 3. So either way, it gives us a 1-3 relationship with the oxygen, so 1,3-dioxane. 4, 5, 6. But notice the green path gives us a 4-methyl, whereas the black path gives us a 6-methyl. So the 4-methyl is clearly a lower number. So we're going to have a 1,3-dioxane with a 4-methyl in front of it. So I'll use green since that was the best path. 4-methyl, 1,3 for those 2 oxygens, dioxane. Okay, so another famous ether that is huge, and we saw this kind of briefly at the beginning of class. This is what are called crown ethers. And so these are really well known for being useful for what's called host-guest chemistry. What does that mean? That means something is the host and it will hold a guest. So the crown ether, as you might guess, is a very large cavity in the middle with, let's draw those lone pairs on the oxygen, all that electron-rich region pointing toward the center. And it will attract something with a positive charge. So it has a kind of a delta minus going in here. So if you have something nearby with a positive charge, it will actually make it into the cavity. So it's even used sometimes to extract cations. I actually use these extensively in my PhD to take advantage of its host-guest properties to make some kind of interesting shapes. I'll show you one on the next slide because its chemistry is still very widely studied. How do we name such a huge ether? So there's 2 parts to the crown ether. There's the carbons and the oxygens. So we count the oxygens. That's part of the name. 1, and it doesn't matter which direction we go. 2, 3, 4, 5, 6. So 6 oxygens. And now notice that in between each oxygen, there are 2 carbons. So it's these ethylene units. All right, so how many of those did I circle? I did it 6 times, so that means we had 12 carbons. And we had 6 oxygens. And so that means we had 18, so let me put that here so we don't confuse that for 60, 18 atoms total in the ring. So we have all the information we need to put that together for the name. And we say this is an 18 crown 6. So there are lots of sizes of crown ethers. I worked on one that was 34 crown 10. So it could be very large, smaller, and how do you know how much it is? It's how many atoms are total in the ring. So my 34 crown 10 had 34 atoms in the ring, but 10 oxygens. So this is 18 atoms in the ring, 6 oxygens. How can we get to epoxides? Well, we already know how to make them. So what we're going to do is just review what we did to make them. Okay, so epoxides are made from alkenes, right? So that one has a methyl, so I'll make sure there's a methyl in there. So something like MCPBA would give us that epoxide. But we also learned we could do an internal SN2, make a red one. So we could have had our leaving group and our alkoxide, and it can go attack from the back and kick off. Or we could have had the other side be the leaving group and this side be the alkoxide. And so that would go attack, kick off. There we go. So these are both similar in that they're internal SN2s reactions. You know, it's basically an internal Williamson ether synthesis. And so you've been doing, like I said, you've been doing Williamson ether synthesis. We just haven't been using the name, but it comes out more in this chapter. So between the two internal SN2s, once again, if you're doing SN2, you can ask which one's better. We always like a primary alkyl halide. You have to take a step back. Is one of these primary, red or green? So hopefully we all vote for. I'll label it if you're in doubt. So green has a secondary alkyl halide, that's a primary. So that would actually be, this would be the more effective of the two internal SN2s. So I'm going to write here, the red path is best, better yield for SN2, and that's because that primary alkyl halide. Now we might recognize I'm just trying to think back, connecting these in a synthetic picture. What would be the starting material for that reaction? So if we see an epoxide, we know enough information to say, and this isn't new, well, that came from this. Okay, if we're not doing the alkene, right? And then what did this come from? Well, that used to be protonated. We never just land on a charge. Usually we like to have a nice clean neutral product. And so then we say, okay, well, what do we call that? That's a halohydrin, right? Halohydrin. Those always come from a alkene. So clearly 1-2 steps, halohydrin formation, base, then the SN2, and this is a little faster. That's a little more straightforward, but either way, we have more than one way to get there. So far in this lecture, we have named ethers and talked about their physical properties a little bit. We've also talked about reminded ourselves on how we've made them. And we've actually have not really done a new reaction yet. We're going to start trying to think about how we can react them. And to do that, we want to take some time to look at their structure and see what would we need to do to make them more reactive. In other words, ready to react, so we can convert it to another sort of functional group. I realized I forgot to fill this in. Halohydrin. There we go. Okay, so what kinds of reactions can we do? So in other words, we want to be able to have a roadmap at the end of this with arrows coming out, and how can we make these more reactive? Well, look at the nature of the structure on the ether and the epoxide is that we have lone pairs there, and it makes it very electron rich. Electron rich just kind of begs for an acid sometimes. So we're going to see a lot of acid-driven reactions with ethers and epoxides. Epoxides are particularly reactive anyway, just because of that strained ring. But let's imagine throwing an acid at ether. And now we have something that used to be pretty stable is now much more reactive. So that's how we can imagine cleaving the ether. In other words, breaking that bond between oxygen and carbon. Epoxides, remember we have this is a sp3 hybridized carbon, and its ideal bond angle would be around 109.5 degrees, right? But because it's part of that three-membered ring, it's closer to 60. So that strain means it's already very easy to react. You actually don't have to add acid to react it. That just makes it even more reactive. But you don't have to wait around for it to get protonated. You could even open it under basic conditions. So we will examine both of those options. First, let's take a minute and look at the first scenario we mentioned, which was ethers with acids. So as we predict from the previous page, we should expect to cleave the ether. And so that means it's going to have, since we're using HBr, that means once we break apart this bond, we're going to either break it here or here. And so I'm going to draw the product. We're going to show that we need the mechanism to understand why. Okay, so remember what I just did on the previous page was have look at the structural features of the ether and notice that there's lone pairs. Notice that we threw an acid over the arrow. That means only one thing's really going to happen. We're going to protonate, which means with HBr, notice there's excess, we're going to have bromide go off there as the leaving group. So we have positively charged. At this point it can leave because, so we could go this way, we can cleave the ether, or we could go this way. And so we can break that bond fairly easily because that will give us a neutral alcohol, but we'll still have a carbocation from whichever side we break it from. So let's explore both paths. Red first. All right, so if I draw what my arrows are saying happens, the isopropyl unit keeps the oxygen and the OH. And so notice right here, the electrons land on O, so this is where my carbocation is. I don't even really like drawing it like this, but I guess I have to. a straight line. That's a primary carbocation. We won't see that happen, right? Bad. So I'm going to hope that that's the path we get to disregard, but let's examine the green path first. So if we have the green bond, the green arrow be the path that we take, the bond here is gone, which gives us a secondary carbocation there, and then alcohol with 2 carbons, so ethanol. So time to draw on the green route. So we have our secondary carbocation, not too bad, plus ethanol. Well, I'm going to pursue this route further, and because I don't know about you, that looks a lot better than this one. So we're going to put an X over, the simple X over the arrow means that doesn't happen. And now we're not going to take the red path. So we're not done here though, because we know that we have excess HBr, and Br minus was floating around anyway. So Br minus, and I'm also going to take advantage of the excess HBr in a minute. That means we get to here. So there's one product. That takes care of this guy. But the ethyl bromide, got to keep going because we have excess HBr. And then we learned from the last chapter that adding HBr to an alcohol, so I'm not going to draw the mechanism for this step, converts the alcohol to the corresponding bromide. So there's the whole shebang there. We'll box that up. Okay, so one way to kind of predict it, say, oh, you know, I have to do this quickly. What's going to happen here? You can say, okay, this piece will have a bromide on it, and this piece will have a bromide on it. So let's imagine circling that. This piece corresponds to this piece, and also gets a bromine. And then let's do a different color so that I don't have too many going on. There we go. That one gets a bromine. So we get each of those R groups, as long as there's excess, get a bromine as well. Now we're going to explore epoxides next. So remember we talked about how epoxides are strained, so it's not surprising they can open. And the only way we've actually opened them is to make diols. You might remember making the anti-diol. So many other things can be used as a nucleophile though. But I'm going to put the one you know first. We used basic conditions like hydroxide, and I'm actually going to put that here. Last chapter, it gave us a syn. Why did I say syn? It's anti-diol. Okay, anti-diol. But remember, it could also have been an alkoxide. It didn't have to be a hydroxide. But that's not to say there aren't other nucleophiles. So anything we know that was a good nucleophile actually can work, or it's a reasonable nucleophile. Because they're so strained, it's easy for them to react. So the sulfur analogs also work. And then our acetylide, we can make a carbon-carbon bond to open up an epoxide. We could use a Grignard because that's a nucleophilic carbon. We're familiar with another nucleophilic carbon, cyanide ion. So these all come back. We also will see more hydride sources that we didn't use as frequently in the beginning. We call them, I'll put them in quotes, H-, but they're delivered on the back of something called LaH, lithium, aluminum hydride, aluminum hydride. So for now, we can treat that as a H-, just for concept, but it's not, it doesn't just dissociate as an H-, but it is a hydrogen nucleophile. So lots of other nucleophiles work too, but this is kind of the list you want to be comfortable with. So things that we've seen act as nucleophiles in the past, in other words. I mean, this is not going to be exhaustive, but this is what, we kind of see around the reader and our homework problems. So let's give it a try. Now let's look at some variety. We know this mechanism for the most part, but it's going to make it interesting because we're not just going to get diols anymore. So we have a Na plus Cn minus over the arrow. So this is our cyanide nucleophile, lone pair on the carbon. And then we're going to attack open, and O minus will get neutralized with the water to make an OH. So we'll always have an alcohol and the new group. So there's two carbons it could attack on. It can attack the top and open up. Remember, it's always a backside attack. And so this is a strong nucleophile and basic sort of conditions SN2 scenario. So that's why we do consider the backside attack, and it attacks either the top carbon or the bottom carbon of the epoxide. Now, since this is a symmetric epoxide, really doesn't make too big of a deal, but it's worth drawing out both scenarios anyway, because we won't always be presented with a simple symmetric case. We'll do some more examples of that, don't worry, but it's always nicer to start simple for the first one. So backside attack means opposite of wedge. So it's going to be cyanide, it's going to end up on the dash, and oxygen gets to retain its wedge on the carbon that wasn't attacked. And then, of course, it's going to be protonated with water. I won't draw that mechanism because we are not going to take that much time to dwell on acid-base proton transfers anymore. We're past that. All right, so now we're going to have the green path as well. Let's say it attacked the other carbon. That means the top one was undisturbed, keeps the wedge O-, and we get a dash down here. And then, of course, we protonate for step 2, and we get neutralized on the top, nitrile down here. So it's time to say, what is the relationship of these two? Okay, so did we draw a new compound or the same one again? So we could see these are not the same, right? But however, in terms of superimposing them this way. But if we wanted to possibly rotate, let's see how that would look. So turn that around. Notice the nitrile, yeah, it's upside down, but that's because I rotated it without changing that. Notice that they look in the mirror. So that means, yes, indeed, they are actually enantiomers. So we have to count both as products. All right, that was easy. It's time for hard. Why is this one harder, even though it's smaller? Look, all that was changed here is nucleophile, anionic conditions, strong nucleophile. So we're going to get the same mechanism. However, asymmetric. So that's always more of a challenge. You've got to use some brain power before you go too far in the mechanism. So I'm going to write this out because all these features out, because that's important to keep in mind. So this is strong nucleophile. We're going to call that basic conditions. Okay, that means we're going to definitely have SN2 style chemistry going on here. So let's show that mechanism. I'm going to go with green for the arrow since I used red already. Uh-oh, doesn't know where to attack. It's asymmetric. Which carbon do we attack? So notice I have a carbon that would be tertiary once the oxygen leaves. I'm going to break that oxygen carbon bond. I have one that would be secondary once that oxygen leaves. But notice we are doing SN2. So if we're doing SN2, we always want less substituted. So I'm going to write that out. Less substituted gets attacked. So we have to make that choice right away before I even finish drawing the very first arrow. So I'm not going to attack the one that has a 3 on it. I'm going to attack the one that has the 2, right there. Attack, kick, open. So that's the regiochemistry you don't want to ignore, because then we're going to go down the wrong path. So it's going to look like this. Just keep your sigma bonding framework the same. Otherwise, it's easier to get confused. So notice what I mean by that is look at my single bonds that are in the plane. So all that planar framework stayed the same. And that way I don't have to do too much thinking with my dashes and wedges. I keep my methyl intact there. My O that just opened up is an O- right now. SN2 backside attack. So that means opposite the wedge. means I have my nitrile, my acetylene got attached, acetylide, which is now an alkyne on here, got attached right there. Step 2 gives us the water to neutralize. So put the pi bond there, OH, and methyl. And we're basically there. Nice. Okay, now we can leave it like that. You check your answer somewhere. It's not going to look like that because that's really not how we normally draw our final product with the planar pieces that could be once the ring is gone, or a pi bond, that restricted rotation is gone, it's going to have a lower energy conformation than that. So we will rotate that so that it looks more like a normal. So notice I have an up carbon here. I'm going to keep that here. So it's 1, 2, 1, 2, up carbon here. So why don't we number our carbons just to keep track? 1, 2, 3, 4, 5. So 1, 2, 3, and I need a 4 and a 5. All right, so my 3 is an up carbon in the original and in the final. So there's nothing to change on the dash and wedge there, but 4 is now a down carbon. So that rotates this out so that our triple bond is actually on a wedge now. Okay, so a couple things we need to always point out when we're reviewing a new reaction: the regiochemistry and the stereochemistry. So what happened in the regiochemistry? SN2 less substituted got the bond, the new group. So nucleophile goes to less substituted carbon. Good old SN2 style, right? So that SN2 aspect of the mechanism explains the regiochemistry. Stereochemistry. We need to look at what we got when we were done. Alcohol and new group. Notice the relationship is anti. So I'm going to write that down. Anti, at least as drawn. Why do I say as drawn? Once I start rotating, it doesn't look anti anymore. So remember, this is the O from the epoxide, and this was the nucleophile. And so now they have this wedge dash anti relationship as drawn. Notice if once you rotate, though, all bets are off. These look syn now. But you need to get to the first step properly. And then who cares how you rotate it? As long as you know how to rotate something, it could be anti or syn. If you rotate twice, it's going to be anti again. If you rotate once, it's syn. So the fact that it's anti is drawn will help you work everything else out. And why is it anti is drawn? Well, if you do a backside attack, it's going to be the opposite, right? So once again, it comes down to the mechanism. So nucleophile anti to OH. So that was what we called basic conditions. You see a negative charge, you see a strong nucleophile, then it's going to have that regiochemistry, nucleophile and less substituted carbon, and the stereochemistry, which is anti. Now we're going to consider acidic conditions. So notice that if we have HBr, we're going to have an option to protonate first, which causes even more strain in the ring. So let's do the mechanism before we figure out where it goes. In other words, we're going to ask, do we get the same prediction here where we would have bromine, which is going to be our nucleophile, on the more or less substituted carbon, and will we have that anti-relationship? And so the mechanism will help us get there. Okay, so remember when we see acid in the presence of one of these ethers or cyclic ethers or epoxides, we are going to acknowledge that that electron-rich oxygen is going to get protonated. So then we're going to rationalize what happens from already being a strained ring to a very strained ring. Oops, I didn't draw my proton on there. There we go. So now that oxygen even wants to detach even more than it did before. So, in fact, it's so strained, we can say it starts to open. It just starts to detach on its own. Just like an SN1 with a good leaving group, which this is, it just starts to let the leaving group leave. So if it's going to start opening, and which means it's going to break either here or here, we have to say which carbon is the better one to leave from. So after that leaves, we would have a tertiary carbon here or a secondary carbon here, and if we let it go before a nucleophile attacked, it would be a carbocation. So let's just draw which one of those we would like to see. We're going to pick it now, is the better carbon to become the carbocation. Well, we know tertiary would be the better scenario, right? So let's just draw a bond partially starting to break, because I'm going to let you know right now it doesn't happen on its own, but it's kind of close to it. So I'm just going to draw like that. So we still don't have a full carbocation because the bond is still intact. It's not severed, so it maintains and preserves that stereochemistry here. However, it is weakening and lengthening, and as it does that, increases the delta plus, or decreases the electron density, I should say, which makes the delta plus more significant here. So it's more electron deficient now, which means, electronically speaking, that bromide we had just formed is much more attracted to this carbon than this carbon. That's the opposite of the basic conditions. In basic conditions, the nucleophile, which is what the bromide actually is, right? In basic conditions, the nucleophile goes straight for the less sterically hindered one. In acidic conditions, the nucleophile is going to go for the more sterically hindered one, because that gives us a better carbocation. And that's because of this simple thing the proton does. It strains the ring so it starts to open, so that we have an electronic effect here where the bromide wants to go here, where there's some more carbocation character on that carbon. So let's draw the arrow showing that. And so it selectively goes there. So I'm going to write that out in words. Nucleophile attacks the carbon delta plus. So the better carbon. So better would be not a true carbocation. Okay. However, because the stereochemistry is maintained, it's not going to attack from both sides like if it was a carbocation. It's going to strictly attack from backside attack, SN2 style. So nucleophile attacks the would-be better carbocation from the backside of epoxide. So whatever the epoxide is, the new group's opposite. So this is a SN1 feature, this whole carbocation consideration. This is an SN2 feature. So this is called a hybrid SN1, SN2 mechanism once again. Hybrid SN1, SN2. Unlike basic conditions, which is pure SN2, this is acidic condition gives us the hybrid approach. All right, so what does that mean? Our final product is going to have the stereochemistry preserved on the carbon that did not get touched, of course. And now we have a methyl and a bromide to draw in, and we need to be careful with stereochemistry. Bromide came in opposite what the epoxide is. That means the bromine has to be on a wedge. This is a wedge. Has to be on the opposite, has to be on a dash. Methyl can no longer be on that dash spot anymore. It pushes it forward. So the methyl will now be a wedge. So we get that inversion characteristic of SN2. Let's see. The bromine is there. Okay, so we're going to summarize that right here. So what is the observed product of the reaction when it's done in lab, right? That's it. So how do we explain this? Stereochem. The real meaning is the SN2, SN1 hybrid mechanism. Just so I answer that question before I wander off and forget, hybrid mechanism. So the feature of the SN2 is depicted in the stereochem. thanks to the backside attack, the anti-OH, the OH is anti to the new group. So notice that relationship here. These are anti. And then the regiochemistry. Which carbon got attacked, in other words? Because the epoxide is part of a 2-carbon functional group. So the nucleophile lands on the more substituted C. Okay, so once again, step back. Compare that to basic conditions. Nucleophile goes on the less substituted carbon. Nucleophile goes on more substituted carbon. Acid and base conditions are opposite regiochem. Stereochem, new group anti to OH, new group anti to OH. Acid and base conditions have the same stereochem. This is hard, believe it or not. It requires the mechanism to solve it. The mechanism explains it all. So when you kind of remember, oh, I'm strained, it starts to open, aha, that's going to go where it would be better off opening, right? So work through these mechanisms a couple times. Okay, if you feel ready for this, these are example problems. This is not a new reaction. This would be a great workshop problem. We're going to do them now. Pause, predict the product, and restart the video after you've drawn the structures for both of these. What are we doing here? We're doing basic conditions, acidic conditions. Draw what the different products would look like. And so I am going to do these a little more rapid fire fast because we've already gone through mechanisms together. So what you want to do is when you see an epoxide, identify what's going on over the arrow. Na plus, OCH3 minus, that means we have a strong nucleophile. We're going to call this basic conditions because strong nucleophiles also make strong bases. H2SO4, clearly acidic conditions. So what does that mean? Basic means we have the SN2 style mechanism. Acidic means we have the SN1, SN2 hybrid. SN1 regiochem, SN2 stereochem. SN2 regiochem and stereochem. Okay, so let's draw our product without having to necessarily draw every little step of the mechanism. We can talk through it. So the parts that I need to talk through are which carbon gets attacked first. Actually, only the other one never gets attacked. So we have to look at the substitution. We're always going to look at the 2 carbons and label them as, primary, secondary, tertiary sort of thing. So I look at this one. I say, okay, when that oxygen leaves, it'd be secondary. When this oxygen leaves, it'd be tertiary. Okay, let's see. It already is that way because that last bond is an oxygen. So this nucleophile, when it comes and attacks, it's going to do SN2 style only because we're in basic conditions. It's going to want the least sterically hindered. It's going to go here. That's the regiochem. And then from there on, we know to make sure it's anti. Okay, so now we know the new group goes on the bottom carbon and it's anti. So, let's do black. Anti means it's a dash this time. New group is a methoxy. Top carbon is unaffected. All the stereochemistry stays the same. It's where the OH ends up. All right, let's do this again. Acid conditions means we protonated this. I recommend you stop and draw the mechanism and make it match the previous page. I'm going to walk through it sort of mentally. So imagine this protonated. Now it's strained. That's when we get to the SN1 part of it. We're going to start letting the leaving group leave, and it would rather leave from this carbon because that's more substituted, hence the better carbocation. So because it starts to leave there, that means this carbon stays unaffected, not attacked, keeps the OH on a wedge. So I'm going to draw that and get that out of the way. OH on a wedge. All right, top carbon gets the new group. That means this bond starts to break. However, still backside attack. Who is our nucleophile? It's going to be our methanol. Attack from the back. Eventually neutralize to get rid of that H on there. So that means we're going to have attack from the back. OCH3. This is the part that ends up on there. Pushes forward the isopropyl. Okay, I'm going to write, do this mechanism for your practice. Especially if you didn't already get that product. Okay, so notice the difference. OH stayed on more substituted carbon. OH stayed on less substituted carbon. Okay, throughout this chapter, that's one of the harder parts, is the acid versus basic opening of epoxides. So get that straight. Practice, 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 lots of nucleophiles. We're going to switch gears a little bit and do another fun application of epoxides. It's fun when you can see them apply to the real world. I'm going to add a functional group on, or just a substituent, so we can kind of see what's going on there. But when you buy, if you've ever bought an epoxy glue, that's because they're named so named epoxy glues because they have epoxides in there. And so the resin, they come in two separate parts. We have the resin, which is the prepolymer, which is the epoxide, and then there's the hardener, which is a base or a nucleophile. So one popular example of a hardener is an amine. So how does this work? Oh, actually I had it drawn here. There we go. We're going to draw that reaction. So let's take our nucleophile. And I said we're switching gears, but it's not really, because that's what we were doing in the last several pages. And let's take excess, of course, epoxide. And our nucleophile would attack and open it, right? Attack, open. So what does that look like? We get the hardener, which has attached itself onto one end of the epoxide. And our epoxide has a dangling oxyanion. However, because we have excess, in other words, the ratio of hardener to resin is not 1 to 1. I'm going to call this A and B. And then we'll have R prime again. We have excess of that epoxide. The nucleophile that was originally there is all gone. However, as it attacked, it created a new nucleophile. So the anion is the nucleophile. So let's let it attack and open. Notice I'm attacking the less substituted position because this is strong base conditions. So we have the terminal end where the little bit of our hardener was present, and we have the R prime. And so then this oxygen attacked, and we have R prime again, and we generated a new oxyanion. And I'm going to draw the AB over again. So here's AB. So this was an AB carbon, AB carbon. So look at that pattern we're starting. ABO, ABO. So look at what's going to happen if we do that again. Maybe you're coming up with a word in your head for the type of reaction we're doing right now. I'm throwing in another equivalent, AB, and it's going to attack the less substituted carbon, SN2 style, open it up. And let me get myself some room over here. All right, so this gets bigger and bigger. It's growing. Oops, this was our group. AB with R dangling down, prime, O. AB with R dangling down, prime, O. AB with R dangling down, prime, O minus. So I think we might get the idea that this is a repeat pattern, right? So we have AB with the R group, AB, R group O, AB, R group O. So I can circle these repeating patterns. They're called a repeat unit. So A, R, and then I got my O. So this is a repeat unit. What I'm doing is I'm taking those units, mer, if you will, monomer, so, and I'm making a polymer. So we're doing an anionic polymerization because the anion is the nucleophile, anionic polymerization. So that's what, nanoscale properties manifest themselves with changes in the bulk properties. We've seen that epoxy resins, before they get mixed, they're liquid, and then they harden once they're polymerized. Polymers are usually solid. Large molecules are solid, smaller molecules aren't always solid, right? So, or more often not. So the bigger a molecule gets, the more likely it is to be solid. So polymers, plastics and things are solids. So we keep going, and we can have however many we had available. So the way we draw this polymer, you'll want to be comfortable doing this. Once you see a repeat unit, you're going to have the brackets, and you have to show one repeat unit. So they can come out of the brackets, and I have that one. So this is A, B, R coming down, O. And then it leaves the brackets before it makes a new bond. So you don't want anything to repeat within the bracket. A, B, A, B, O, and that R prime hanging down. Don't repeat any more, no more A's and B's in the bracket. And we say that repeats n times. Now, these little end cap guys that came in from a smaller equivalent, those are often left off, because the main part of the polymer that keeps repeating over and over again, once you identify the repeat unit, is what goes in here. What goes on the end here could vary. So this is a repeating polymer for this unit that comes from an epoxide. I'll write that here, repeat unit. So our monomer was this guy. And so this is our final polymer. So that's pretty exciting. We did our first polymerization, and that is a nice note to end on. I have one more slide from one of my favorite chemistry authors that's from really old school. I like a lot of this chemical history. I'll leave that quote with you to ponder on. You might be able to relate to it by now. When in the dark province of organic nature, we succeed in finding a light point, appearing to be one of those inlets whereby we may attain to the examination and investigation of this province. Then we have reason to congratulate ourselves, although conscious that the object before us is unexhausted. What does that all mean? Well, we might be in the depths, studying really hard, trying to make sense of all of these reactions and connections of the organic nature, and then we find a breakthrough where we've made a connection, right? And we say, okay, there's an inlet where we have attained sort of knowledge and we think we understand. But the more you understand, the more you realize there's more to not understand, right? The object before us is unexhausted. So there's, nature alone demonstrates that. All right, so I will leave you here. Hope you found the musings of Professor Justus Liebig enlightening, and go forth and have fun opening epoxides.